To calculate probabilities with the normal distribution, we need to calculate the area under the curve on some interval. And that interval will be determined by the probability statement that we want to evaluate. So for instance, in each of these three examples, we're given just generic values A and B. We want to take these probability statements, turn them into a shaded region to represent the probability that we'll be calculating. So in part A, we want to find the probability that some value x is greater than A. So assuming that our point A is here along the x-axis, we want the probability that x is greater than that, meaning we want to shade the area under the curve above that value A. And keep in mind that this shaded region continues to extend to the right because this curve heads off to positive infinity. So the probability that x is greater than A is represented by the area of this shaded region under the curve. If we want to find the probability that x is less than A, then we'd be looking to calculate the area under the curve to the left of A. And again, that shaded region just continues forever since this curve is headed off to negative infinity. And if we want to find the probability that x is between A and B, then what we're going to be calculating is the area under the curve between those two different points. So we're going to find the area of that shaded region. In this case, instead of heading off to positive or negative infinity, isolated specifically between those two values, A and B. So let's take a look at a few examples. First, we'll set up the probability statements, shade the graph to represent what we'll be calculating, and then we'll flip things over to StatCrunch to see how we generate these results. So the first question, research has shown that the mean length for newborn seals is 29.5 inches. The standard deviation is 1.2. So for normal distribution problems, we'll always need that mean and standard deviation. We want to find the probability that a randomly selected newborn seal is shorter than 28 inches. So we want the probability that our seal pup, represented by that x, whatever our measurement is going to be for the one that we select, is less than 28 inches. So in this case, our mean is 29.5. So the mean is always represented as the center of that distribution. So our value of 28 is a little bit less than that. Probably should draw that even a little bit closer, but we've got a value that's a little bit less than that. And we want to calculate this area under the curve to the left of 28. In part B, we want to find the probability that a randomly selected seal will be between 27 and 30 inches long, or 31 inches long. So that means we want to calculate the probability that our randomly selected seal will have a measurement that's somewhere between 27 and 31. So again, our median is 29.5. So a measurement of 27 is going to be a little bit less than that. Our measurement of 31 is going to be a little bit more. So we'll want to find the area of this shaded region under the curve between 27 and 31. So drawing these pictures is going to be helpful if you can visualize what this looks like, because when we pull up the normal calculator in StatCrunch, it's going to generate this picture for us along with the probability statement that we input. So it'll be a way to verify and just make sure that what you're calculating matches up with what you should actually be calculating in the problem. In example 3, we have birth weights in the United States, which are normally distributed, with a mean of 3,420, a standard deviation of 495. A particular hospital requires special treatments for babies who are less than 2,450 grams are more than 4,390 grams. So those are considered unusually light or unusually heavy babies that require additional care. We want to know what's the percentage of babies who don't require special treatment because they're in that normal birth weight range. So essentially we want to find the probability that a randomly selected baby will be between 2,450 grams and 4,390 grams. So they're born in what's considered to be a healthy weight span. So this would be finding the probability from 2450 to 4390. And again, we're going to want to calculate the area under the curve between those two values. So now we'll turn things over to StatCrunch to see how we actually do that. In each of these cases, we're not ending up with any sort of nice geometric shape. This isn't really a triangle, not really a rectangle, so there's no simple formula we can apply to this, but StatCrunch has a calculator that will allow us to complete these calculations and find those areas. So coming back to that first example, we want to calculate the probability that x is less than 28, given this mean and standard deviation. So in StatCrunch, we'll select Stat, Calculators, and then the normal calculator. What we need to do is input our value for the mean, which again in this case is 29.5, our value for the standard deviation, which is 1.2, and then we need an inequality statement. In this case, we want the probability that x is less than or equal to 28. And what we generate is this shaded graph that should match up with the picture that we drew. So we have the mean again centered right around 29.5. We have our shaded region starting at 28 and headed to the left. The only thing that's really different here is that the inequality statement here is less than or equal to, but we wrote that as a strictly less than statement, or in other cases we use strictly greater than statements. For the normal distribution, it doesn't matter. A less than or less than or equal to statement means exactly the same thing. So StatCrunch only gives us the option to select less than or equal to or greater than or equal to, but we use those just like less than or greater than for this particular distribution. So this generates our probability of about 10.56%. In part B, we wanted the probability that x is between 27 and 31. So our mean and standard deviation remain exactly the same. To get that compound inequality, we'll select between, and now we can put in a value at both the low and high end. So we want x to be between 27 and 31, with the mean and standard deviation remaining exactly the same. Click compute, we get our shaded region from 27 to 31, and our probability of about 87.57%. In our last example, we have another compound inequality, but this case we now have a different mean and standard deviation, so we'll need to update that. And update the values that we're wanting x to be between. In this case, we want it to be between 2,450 and 4,390. And we calculate that probability, and we get about 95% when we round that result.